Hello everyone, welcome to this week's Crunch seminar. Today we have one speaker. Yixuan Wang will be giving a presentation on data-driven discovery and verification of singularities in nonlinear partial differential equations. Yixuan Wang represented China at the 56th International Mathematical Olympiad and studied applied mathematics at Peking University, where he was the only representative for the national scholarship and was named the Person of the Year. At Caltech, he pursued a PhD in applied math and served as the founding president of the Siam student chapter. With this short introduction, I welcome Yixuan to give the talk. Thank you.
Thanks, Vivek, for the kind introduction, and thanks again, Juan and George, for the kind invitation. So today, my talk, as you can see from the title, it's a little bit all over the place. It's first, it's very important to have a data-driven. By data-driven, I mostly mean like machine learning techniques. The second ingredient of the talk is on like singularities in nonlinear PDEs. So that's, I want to say, the a main bulk of my work during PhD. And yeah, most of the work are done together with my supervisor, Tom Hao at Caltech. He's one of the pioneers in um, singularity formation for in fluid dynamics and also computer-assisted proofs. Yeah, uh, uh, and I've learned a lot of all this and machine learning over the course of my PhD. Oh, okay, now it's good. Okay, so it's actually today's my first time giving this talk. So you guys can feel free to interrupt me and ask questions at any time. It's not a it's a very preliminary talk, but I hope I'm gonna be able to convey all I want to say. So it's roughly structured into four parts. The first part, I'm gonna talk a little bit about my research overview, the most important message I want to deliver here. It's a really you want a synergy between computation, which can be like traditional numerics or like machine learning techniques, and the proof. So you need a math to guide your numerics, but most importantly, your numerics can also guide your proofs. That's the overarching theme of my talk. The second part is more about a particular a motivation. It's a very famous problem, the Clay prize problem. I'm like nowhere close to that problem, but it's a motivating example and help set up the settings for the numerics and proofs I'm going to be talking about. The third part is actually a little bit of a detour on a case study of a proof. Again, the proof is inspired by numerics, but why I want to include that? Because two things. First, I really want you guys to appreciate that the proofs can be like extremely simple. Like it's not very sophisticated. Like with the right intuition, anybody can do it. A second, this actually highlights where machine learning techniques uh, are different from traditional numerics because a lot of things traditional numerics can do, but there are some cases where really machine learning are at the core of it. Yeah. And finally, the last part, I think it's more focused on our recent preprint. It's we call it high precision pings, and with a particular focus on singularity formation. Okay, without a further ado, I'm starting to give a overlook of my research. So the first part, it's like the a level of math and numerics. They're sort of inspired each other. One of the works I did with my co-author and friend Zimin Liu from MIT. It's called a Kolmogorov-Arnold network. it has a lot of impact in the AI for science community, I think. The punchline is that I'm not going to be talking about that today, but the punchline is you want to use more complicated learned nonlinearities in your neural network architecture to be able to have a more expressive but also more interpretable uh, representation for your underlying function. The okay, so the other way around. So this is the main bulk of my thesis. Actually, it's how numerics can inspire proofs. So again, like Kant, it's inspired by the a mass theorem, the Kolmogorov-Arnold representation theorem. But on the other hand, what we observe in numerics can also bring some new insights in proofs. So this a series of work is what we establish singularity via a local orthogonality in a dynamic rescaling of time. So there's a lot of jargons going on. I'm gonna unfold a bit of this in the third section. As I promised, it's gonna be extremely simple. But the punchline is that we are able to establish singularity with clear stability, with rates automatically inferred, and we don't rely too much on explicit spectral information. So this is a framework I think very nice to apply to computer-assisted proofs. I'm going to talk about computer-assisted proof in a few slides as well. We establish a self-similar, problem beyond self-similarity for full stability, and some problem with implicit profile. Okay, so the first two parts are at the level of heuristics. The next two pages are like a serious business. So like we first we really need high precision numerics for gaining insights in like mathematical proofs. Again, I'm gonna unfold that in the next few slides. But like so particularly it's about we use machine learning to search for blobs. So kinds, as I've explained, because it's interpretable. So one of the earliest motivations for that is a symbolic search for blobs. And then we have neural operators. We build on neural operators with Anima's a group to also work on blobs. And finally, this is a paper I'm going to be talking about today. We build on high precision pings of blobs. The neural operators work and the pings work. The search for blobs are inspired by a very important paper published in a PRL, which I'm gonna talk about later in today's talk. And finally, just to show you guys, we're in a serious business, so it's not just at a level of computation and heuristics. We can actually use numerics to make proofs rigorous, and it's very important proofs. So this is our work almost finished with Tom and a student, Jonathan Young in our group. I think he's really the main guy. He spent like 2 years on all of the sophisticated numerics. So essentially, we linked the important problem of non-uniqueness of 3D linear stocks to a particular setting of solutions with unstable eigenvalues, and we use sophisticated numerical procedure to like construct approximate solutions with the desired properties, and then it's very complicated, but we are able to establish that rigorously. Again, I'm gonna so this is not the main focus of the talk, but I'm gonna share some of the philosophies in a few slides, and also this idea of computer-assisted proof of combining high precision numerics with rigorous proofs is not done by pioneered by us. It's been in literature for a couple decades, I want to say, and I'm happy to see that a lot more like pure math PD analysts are nowadays leveraging computational tools, especially machine learning, to do like a rigorous proofs. This work, however, has nothing to do with machine learning. Okay, that's so much for the whole overarching scene. And now I'm gonna talk about the particular motivation, a Clay prize problem, and our setting of self-similar blow-up, which is also the setting of our high precision pings paper. So this is a famous Navier-Stokes equation in three-dimensional incompressible. It depends on which community uh, you're talking about, but in the math community, the other way we present this problem is just like on this one page, a slide. So you have a velocity field, you have the nonlinearity, a nonlinearity on the right hand side, then you have pressure, and you have a diffusion. And of course, you need to satisfy the divergence-free condition. In the case of no viscosity, this is Euler equation, and in the case of positive viscosity, it's Navier-Stokes. And when we talk about a blow-up or equivalently singularity formation, it basically means that a certain quantity of interest is gonna, its infinite norm is gonna tend to infinity within a finite time. So as small t tends to time capital T minus. So a very famous one of the seven Millennium Prize problem in math is whether this equation one is going to be a globally well posed for smooth or nice initial data, or it's going to demonstrate a finite time a blow up, and it's going to be posed on the whole space. So what we and actually the whole literature of a blow up, I think being interested in is the so-called self-similar blow-up. It's basically, it's a very structured singularity with a lot less degree of freedom. Basically, you can think about this as similarly to a family of Gaussians. Each Gaussian is a rescale of the a unit, a Gaussian. So this is similar. The function f of t and x, it's a rescale of a function capital F that is independent of time. And it's clear by these answers as time t tends to capital T, is gonna, the infinity norm of small f is gonna blow up. So in this line, one of the, I want to say one of the most important recent contributions, it's by Tom and his former postdoc, Guo Luo, like yeah, almost 15 years ago. They provide a very compelling numerical evidence for a blow-up for smooth Euler equation, but it's with boundary. And this work inspired a lot of works in the PDE fluid community to come up with some very important proofs. And finally, like a few years ago, with his former PhD student, Ajia Chen, they were able to establish that proof rigorously. So a couple of 15 years ago, it was compelling numerical evidence, but they're able to prove it rigorously with, again, computer-assisted proofs. So one of the first works I've done with Tom is basically we study some a 1D problem concerning the interior blob of Euler slash Navier-Stokes, because now the problem of Euler with boundary has been resolved. So maybe we can take a look at the interior blob on the whole space. Just a disclaimer, there's a couple of works, including the recent numerical works by Tom, suggesting that depending on the appropriate assumptions, the Euler slash Navier-Stokes might not have self-similar singularity. Nonetheless, self-similar singularity is a way to start. Okay, so that's a lot about the backgrounds. Just to be a bit more concrete, we can just look at this very simple example of the Burgers equation. It's simple, but it's simple enough, but still conveys a lot of message. So we have this 1D inverse of Burgers equation. again, again, everybody in the PDE community should know, and it's actually it's a gradient is gonna blow up a knot itself, so it's developing a shock instead of a singularity. So here again, if we plug in this self-similar ansatz, this small u, we plug in the capital U and we set the blow up time to be 1, so capital T equals 1. So if we plug in this self-similar answers, we transform this small x in the physical space to the y variable in the profile space, then we get an ODE of the profiles. So again, we're reducing a 1 plus 1 dimensional problem to a 1D problem. And what is even nicer is that the original equation is going to blow up or develop shocks, so it's very hard to capture numerically. But this profile ODE, the solution is actually going to be very smooth and bounded. And the goal for us for this problem is very simple. People can have implicit solutions. But for more challenging problem, it's a similar thing. The goal is to solve this profile equation to high precision in the whole space. Because if you solve the original singular problem, machine cannot compute infinite values, so it's going to be super challenging. But the self-similar answers are going to help to reduce to a nice problem of the profile. A quick remark is this lambda, you don't know a priori, so you can think of it as sort of a flavor of an inverse problem. So you're inferring, and also it's a sort of resembles a abstract eigenvalue problem. So lambda is the scalar eigenvalue, and U, the profile, it's a infinite dimensional eigenvector. So yeah, I'm just gonna pause for like 10 seconds to take questions about the settings. Okay, that's great. So the third section is a bit of a detour, contains a bit of math, but I'm like again, I'm trying so hard to say that the math is like a simple once you have a correct intuition. It's based on a tool example of one of our theoretical papers, but it's simple enough. And also at the end of this section, you're gonna see that traditional numerics are like really really good. Why do we need machine learning? That's gonna be addressed at the end of the talk. Okay, so it's a bit of a detour. So think about this equation. It's called the semi-linear heat equation in one dimension. So the spatial dimension, x is one dimensional. So you have this phi t equals Laplacian phi plus phi squared. If there's no nonlinearity, then it's the heat equation. You know it's gonna be like pretty nice. If there's no diffusion, however, if just phi t equals phi squared, that's the Riccati ODE. And you know it's one of the simplest equations that is going to establish singularity. You can have a explicit solution. It's like 1 over 1 minus t, and you immediately see that it's going to blow up at time 1. So yeah, just to illustrate a bit about our dynamic rescaling formulation, it's pioneered by I think a lot of people in the community, but recently pioneered by Huang De and also Jiajie Chen. Both are former PhD students of Tom, and also by Tom, like all three of them. So basically, what's doing is that it's doing a nonlinear rescaling in time and in space. So you have to t, you rescale t time t to the a rescale time tau, and you rescale a physical variable x to a rescaled variable z. So this rescaling is closely linked to a profile equation. So in a limit tau tends to infinity, this is going to converge hopefully to the approximate a profile. So once you have that, you plug it in, you do some like a simple algebraic manipulations, or you have this PD of U, because we're not looking at the steady state. There's still a U tau. So U tau, it's almost the same as this original equation with two scaling terms, and you also have a scaling factor h over d squared on the a Laplacian term. And you know this is going to have approximate profile of this form. And again, what is amazing about this formulation is that once you've done it, you see that a diffusion term formally is negligible, and the rescaled nonlinear heat to the leading order is just a Riccardi equation. So this is just a Riccardi profile with a Riccardi scaling. But then it's not the end of the story, because we still have this diffusion term. How do we compute and how do we prove it? Okay, the simple thing is, again, why we call this proof is inspired by numerics, because numerically we want our computation to be stable. So what can be a stable trick to do? We just enforce the perturbation to satisfy some like a local vanishing condition. So this is the punchline. We call it modulation via local vanishing conditions. So we basically linearize the solutions around the profile. And for the perturbation, we denote it by a W. We enforce it to be even, and we have some vanishing conditions. So it doesn't perturb the scaling asymmetry terms. Once you done that, recall you have 2 degrees of freedom of the scaling parameters CW and DW, and you have 2 constraints. Okay, voila, you solve the ODE and you are basically done. So once you solve this ODE, you can solve the CW and DW, and you get a ODE of this scaling parameter lambda to the leading order. A lambda is just 1 over tau, which is 1 over a log capital T minus T. So this has 2 meanings. First, the viscous terms, because its magnitude is magnified by power of lambda, so it's indeed small. So we can treat it perturbably. Secondly, you automatically infer the log correction, this 1 over log capital T minus T, which is, if you just want to compute a brute forcefully, this is impossible, because it's a very fine scale correction of a log order. But if you do this algebraic tricks, you get it almost for free. One last step is, how do you actually prove it rigorously? You basically do some singular weights, do some singularly weighted energy estimate, characterizing the vanishing order of the perturbation, and you get a bound of this form 6. Okay, why do I show you guys this very detailed formula? Because this form 6 is actually one of the cornerstones of a rigorous computer system proofs. So recall that here we have an explicit profile. So the small parameter lambda is the small parameter in front of the viscous term can be made as small as we want. But on the other hand, if we only have an approximate profile of what is a reasonable final estimate we're gonna get, it's very similar. It's of this form, E tau smaller than minus CE. This is the a linear stability, the a linear damping, and then plus the epsilon. This epsilon is related to the approximate solution, and then you have a nonlinear term. So again, sorry, I'm going this extremely fast, but this is the high level idea. Again, it's not pioneered by us, like people in the community know it, but that's basically what you're gonna get. And so it sounds like so mysterious, like how can you upgrade numerics to rigorous proofs? But it's just simple. So here's a very provocative title, but how? Like conceptually it's hard, but how do we do it? First, we got an approximate solution with very high precision that renders a sufficiently small epsilon. And because the profile can be constructed by some spline interpolation, so you can rigorously control the residual, like not just numerically, but rigorously using interval arithmetics. And so that's the first step. that's where all of this machine learning or traditional numerics is going to come to a rescue, because simply we just don't have a explicit profile. The second step is the stability, and the second step is almost a disentangle from the first step. The stability part, you really need pen and paper, you need mathematicians to work it out. What we demonstrated is some like singularly weighted estimates, but there can be other approaches. So stability basically, it's basically this. You require the initial data close to your approximate profile to remain stable in the profile equation. That's really challenging. Yeah, so that's basically the high level idea of computer assisted proofs. And finally, in this section, I'm just gonna show you a numerical results. This is by a traditional method, by the time rescaling method, by our enforce of stable local modulations. We show that even from large initial value, this rescaling is going to be able to converge the profile like really fast, and we can capture the a log correction. Like this is amazing. Like why do you even need machine learning? Okay, I'm gonna put a hook here. I'm gonna explain in the next slides. But basically, this page shows you for this particular semi-linear heat equation. It's very simple, but traditional numerics with a bit of intuition of this local conditions works like a charm. Okay, so this concludes this section on the computer assisted proofs and also how you use traditional methods to solve the profile. I'm gonna pause for like 15 seconds to take questions. Okay, great. I hope the last section's math is not too confusing for you guys. Finally, we're talking about machine learning for a blow-up profile computation. So this is a one-page a philosophical slides on the use of machine learning. So again, to start, we ask the question, why do we even need computation? Why do we need computer-assisted proofs? Well, that's simple because the profile of interest is intrinsically high dimensional. So for semi-linear heat and burgers, it's like a one dimension. Mathematicians have all the tricks to tackle one-dimensional problems. But for example, for this very simple 3D axiomatic Euler, well, this is a simple, quote unquote, simple in terms of a dimensionality because it's only essentially two-dimensional. The thing that a Tom and a Golo and a Jiajie are concerned, it's in terms of dimensionality, it's only two-dimensional, but in terms of the challenge, it's like immense, like impossible. At least what we think it's impossible for like pen and paper proofs. But why do we need machine learning? Because in the Tom's computation, he never uses machine learning. He just used this dynamically rescaling of time. Okay, so this is the very important message from this very important physics review, a letter paper that I mentioned in the very beginning of my talk. It's done by a collaboration of a few physicists, Yongji Wang, Qingyao Lai, and two mathematicians, Javi Gomez Serrano, who is a professor here at Brown, I think, and also Tristan Buckmaster. So a very important observation is that some profile, and particularly some profile of interest, are unstable if you use the time marching. And in their paper, they demonstrated that via a few examples. But of course, so here, one machine learning can come to a rescue. One can combine machine learning with the optimization perspective and perform like a gradient descent. Of course, a gradient descent. There's another problem of the optimization, a landscape, the region of stability, but it's a different problem. So I'm not saying that machine learning has to be better than traditional methods, but at least based on their observations and also some of our observations, machine learning can have a different, it's a alternative and sometimes a good alternative.
Sure. One question. So based on what you said is that there are some profiles that are unstable when you do time marching. But the third point that you're implying is that there are some problems that you can solve with machine learning that you
Yes.
cannot solve with traditional numerical methods.
Yes.
Oh, okay. And that's what you're gonna show in the examples, right? Or
Sorry, what's your last sentence?
oh, and those examples are you going to show us? And
Oh,
that's what you tried for
I
the.
mean, for the previous, okay, to be honest, for the previous draft of our paper, we didn't include the unstable profiles, but in the upcoming version, we're gonna include some unstable profile. And since those are like a recent numeric, so I didn't include it in the slides, but we have the results, and I'm happy to talk more about it.
Mm,
And also, as I said, our this work is highly inspired by the PRL paper, and in their paper for a simple, not simple, like for a 1D problem, they're able to compute unstable profiles. And even for the simplest Burger's equation, which we do have, like for Burger's equation, it's clear to see that for machine learning, you can compute uh, unstable profiles. A
oh,
great
I see, I
question.
see, I see.
Yeah.
Okay,
Yixuan,
thank you.
Yixuan, actually this paper, the PRL paper you mentioned, Yao Lai gave a talk to our
Yeah.
group like you do before, and so they had extra constraints for pins to work. I remember there was boundness, I think, of third derivative or something like
Yes.
that. Am I
Yes.
right?
Yes.
Okay, so that's an assumption, right?
Uh, so yeah, thanks, George, for the question. Just to clarify, I think uh, if my interpretation of the question is correct, I think what we are saying is that we need to impose, I'm also going to be talking about in a few slides, we need to impose a sublet training. So that's what they're doing. So it's very simple. You want to encourage your solution to be as smooth as possible. So instead of just a mean square loss, you impose the H1 a loss or H2 loss or H3 a loss. The more smoothest loss you impose, the harder the optimization is, but a smoother your solution is going to be.
Right, yeah.
Yeah.
So yeah, that's right. That it's a penalization, the loss. You're right.
Yeah. I think, if I'm not wrong, I think a similar techniques have been employed by you guys
Yeah,
already.
I mean, Sobolev training is one way, but it's not exactly Sobolev training, right? Because they choose one, I think the third derivative to
Oh,
penalize.
okay. So that's more of a technicality. That's more of a technicality because in order to distinguish smooth from a non-smooth for the burger's case, the burger's case, the non-smooth solutions are smooth up to the second order. So that's why they penalize the a third order
Third
derivative.
order, yeah.
Yeah.
For implicit burgers, yeah.
Yeah. Great. Thanks for the great questions. And okay, so as I was saying, our work is largely inspired by their work. And although we say that our work is a lot more digits more accurate and also unstable cases for this a very important boostneck model for the 3D Euler with boundary, they have also before us they have announced the results in a few talks, but they don't have a published version. So yeah, and but the caveat, okay, but another disclaimer is that our work is like, so it's inspired by their work, but there are a lot of different settings. which I'm going to be talk about in a few slides. And our work is more over open source. So if you guys are interested, I'm happy to share the code. And upon publishing, I'm also going to share the code. I think that's a common thing in the community. I'm not very familiar with this community, but that's what folks been telling me. Okay. Yeah. Okay. So essentially, I'm assuming most of the audience knows pings because it's a crunch seminar. So I'm not gonna belabor you guys to the details of pings. I'm just gonna high level a few very important to us. It's very important tricks, and some tricks are already shared by their PRL paper, but some tricks we think is very important. Moreover, we think these tricks are not just tricks, but they can be like principles for like problem beyond singularity formation. That's why in the first place, we named this paper high precision pings in unbounded domains, because just to make pings more accurate, I think it's a very interesting topic that I would personally pursue beyond the singularity formation. Okay, let's talk about the business. The first key idea, okay, it's very it's a very obvious thing, because you're now talking about solving a profile on an infinite domain with high precision. So how do you do that? Okay, so first, in terms of assembling, this is inspired by actually they did the same thing. It's obvious you don't want to do uniform sampling, because that's gonna be intractable. What you're gonna do instead is you want to do an exponential mesh, so that a few stencil points can capture the a mesh with a high enough region. So yeah, that's very important. What we found in our experiments, another I want to say equally important thing, is that you want to enforce far field syntactics accurately. Because normally you think about
Yixuan, sorry, on the first point, what do you mean? For example, the collocation of the Hermite polynomials would do it?
no, but I'm talking about
If I take the roots of the Hermite polynomials, would that be a good would those be good sampling points?
oh no, oh yeah, okay. I think no, George, let me
Because that's the idea. That's the spectral method in the infinite domain. So
right.
cannot do better than that.
Right. Okay, that's a good point. But here, just a very simple, I think, yeah, maybe you're right. Thanks for the suggestion. But here, what we were saying is just a simple mesh. It's just essentially exponential of x. Here, we use the assign edge of x. Why do we do that? Because this is related to the syntactics, because we know that the solution is gonna decay. So essentially, we don't need as much as a far field collocation points. So we want to concentrate more on the near field. But George, you're right. Yeah. I need to think about it.
But that's the roots of Hermite polynomials, exactly like that.
I see.
And it's the optimum distribution.
Okay. Yeah. Thanks for the great catch. Yeah. Thanks. Okay. And yeah, the far field syntactics, because this is what makes it distinct from the finite domain. Finite domain, you have a prescribed boundary condition, but here, essentially, we're doing a cutoff on the far field, and we want the far field to still be faithful. So there are various ways of doing it. The way they did it in the PRL paper, it's what we call a weak context. So it's simple. You just enforce a Dirichlet or a Neumann boundary condition on the far field, on the cutoff far field. But I think this is not ideal, because if we have more decay information, we have more syntactics, the solutions are going to be more accurate. So in the ideal world, we're going to have an exact decay rate. This can be done via like mathematical analysis, if possible. or what we call hybrid asymptotics. So we first get a solution U with a weak asymptotics, and then we extract the asymptotics from a solution and use that as a exact asymptotics for a more accurate solution. So this idea of hybrid asymptotics is inspired by Tom and Ajaj's computation for the traditional methods. I'm going to show you in a few slides that at least if you compare exact with weak asymptotics, the improvement is going to be drastic. The second key idea we found is the importance of hard constraints. So again, what people already been doing, and in particular what the PPRL paper been doing, is to enforce hard constraint in parity. So if you assume your function to be even or odd, you can do this algebraic manipulation to enforce the parity. But moreover, remember here, we are solving from 10 slides ago. We're solving an eigenvalue problem. So a zero is always a trivial solution. So we need to enforce no vanishing conditions at origin. But what we found in our paper is that this condition, if you pose it as a soft constraint, the optimization is pretty bad. So when I talk to folks, I've also talked to Juan, I've also talked to a few others folks in the pin community. They think hard constraint is very important. So what we're doing here, again, it's simple. If you have this sort of a gradient non-vanishing condition, you impose the hard constraint via a tail expansion. So if your omega is exactly of this ansatz, then you are guaranteed to satisfy this hard constraint of non-degeneracy. Empirically, we find that once we impose that, the optimization is going to be much better. A second important piece of ingredient is the optimizer. So here in this paper, we basically adopted an off-the-shelf optimizer. So it was called self-scaled BFGS. It was first developed in the optimization community, but then made popular in the pin community by Jorge and his collaborators in a JCP paper. Later on, with a few folks in George's group, they applied to CANS as well. So essentially, it's very simple twist. They use a scalar rescaling to improve convergence of the BFGS, which is a popular second order Newton quasi-Newton method. Essentially, first order, if you use Adam SGD, the convergence is like also because of the stochastic noises, the convergence is not going to be ideal. If you just think about the Monte Carlo error, but like you really need to go to a second order. And then of course we use the Sobolev training, which they also did. But there's a caveat of this. It's very nice. The residual is extremely small, but this is caveat because they use full batch matrix updates. Empirically, at least based on the compute I have, which is not great, Caltech GPU, it's very hard to scale on a GPU. So that's why I actually use Tom's like Mac Pro from 5 or 6 years ago. It's not a great machine, but it works. So a very immediate question to ask is like, can we do better optimizers? Because optimizer here, as in Jorge's paper, it really matters. Yeah, we can. There's especially recently there's been a resurgence of popularity in like thinking about optimizers in machine learning, not just pins, not just scientific machine learning, but the language models. Also, a lot of machine learning service I've been talking to, they're really interested in like understanding, for example, the famous muon optimizer. It's not even a paper. It's just a blog post, but it's gaining extreme popularity. For scientific computing, we have this SOAP or other methods. And I think it's important to explore also, I think a recent paper by Sifan Wang and some of his collaborators been working on using SOAP to pins. Yeah, so I think this exploration of optimizers, it's very essential to high precision training of pings. Okay, just a few numerical results. First one is the 1D burgers. We have the final residual on the right and loss trajectory on the left. You can see that our weaker symptotics is on the upper panel and the exact symptotics in the lower panel. You can see that it's much better to enforce exact symptotics. It's not surprising because you want to use as much information as you want. And finally, just a few results on the boostnex. So this is the final residual, the L infinity. So basically, the residual plotted on fixed domain of the equations losses is like quite small. Yeah, and that's as much, frankly speaking, that's probably as much as we can afford on the expensive full-scaled, full-size self-scaled BFGS. Yeah, and this is the this is the loss trajectory. You can see that using Atom on the first 10K epochs, it's okay, but like starting to get oscillatory. But the self-scaled BFGS methods really take the residual to like 10 to the -11. So yeah, that's so much for the reporting of the results. And as I've mentioned, similar to their group, we've also identified a few unstable blowups as well. But like, okay, it's on the stocks, the clay problem, it's always there. It's super challenging. I don't think we are close in our group, but I think this powerful machine learning technique to identify unstable blobs can help tackle more equations, other equations of interest, especially coupled with our proof, a framework of proof. I think that's a very robust proof technique, and you can use computers as proofs. So that's in terms of future works. In terms of a better high precision training, besides the optimization thing I've just talked about, you can think of, okay, maybe we can use better architectures, or here in the paper, similar to the PRL paper, we only use a very simple, fully connected network. Maybe you can better architectures, or you can scale up the a model. But here's the thing: right now we're using self-scale BFGS. It's hard to scale this up. Sorry, but you guys, Jorge, you guys might have more comments, but that's my take. I love the method, but yeah, okay. And finally, there can be other tricks. You can do boosting, or like learn a few networks progressively. You can do frequency encoding. Many of the tricks, I think, they're not specific to pings. They're not specific to singularity computation, but I think the Qin Yao and Yongji, a few of their group, have been exploring those tricks to like high precision computation. With that, I hope I know I delivered a lot of stuff and I'm slightly over time, but I hope I'm able to convey my message and to convince you, okay, proofs are not hard, but proofs need numerics. And pings, machine learning, it's a good, if not a great, alternative to traditional methods. I mean, sometimes I still like traditional methods, but pings are really good. Okay, thanks, guys.
Thank you, Yixuan, for presenting your work. We can now open the floor for questions.
Just one point about the scaling. I think Jorge is here actually in our group now visiting, but also Raj Shukla, if he's here, he is developing a library that does mini batching for this second order, for the BFGS, self-scale BFGS. Raj, are you there? Maybe he's not.
Yeah, that's very nice because that's
Yes,
also
I'm
one.
here. Yeah,
Oh,
I'm
Oh,
here.
here. Raj, can you say anything about the library you're developing and the scaling up of self-scaled? We cannot hear you, Raj. I don't know you.
Yes.
Yes.
What
What
I'm developing basically just adding batch. Just one method which was proposed by Nosedal, like where you have some overlap between the batches, and you can reduce the minimization of the noise actually. And I tested on for SSBFGS, and it scales very well and with same accuracy. So that's all about batching with the SSBFGS. You can do that. But with existing implementation, I have gone up to 100,000 parameters. So I'm not sure how big your network is.
200,000. Is that
100,000.
100,000? Oh, okay. That's very good to know. Yeah, thanks, George and Raj. Yeah, that's why I wanna give this talk because you guys are leading experts in pings, and particularly recently you guys also work very hard on this. I mean, not also. You guys work very hard on this optimizers. I'm just using it off the shelf. Yeah. Thanks.
Yeah, just I had a question on the where you mentioned the asymptotic implementation. So if you don't have damping, then how you would impose the far field asymptotic here? Yeah,
Oh,
if you
sorry. What do you mean by damping?
so you mentioned that the decay rate, right?
Oh
If you
yeah,
don't
yeah.
if you don't have decay rate, then how would you impose it?
Yeah, that's a good question. So basically, here's the thing. Even if you don't have an exact a decay rate, for example, by exact decay rate, I mean, okay, I know the far field is gonna be of x minus 2 plus a y minus 4 or something. But if you don't have an exact decay rate, you still know from your mathematic hats that the function is gonna be of at least order 1/r. Like it's gonna decay faster than the order 1/r, but you don't know the exact decay rate. How do we do? We just do a zero or a Neumann boundary condition or a zero a Dirichlet boundary condition. That's not ideal, but that's a something.
Okay. Okay.
Raj, think of the Coulomb forces,
Distance.
right?
Yeah. Oh, yeah.
One
Yeah.
R, 1r square, and so on. So yeah.
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 So, because the one problem is that if you remove the effect of the decay, then it should recover the input source, right?
Sorry, say that again.
Ideally, like if you just reduce the effect of the decay, then it should recover the source, right?
Oh yeah, a great question, Raj. Here we don't have a source. Yeah,
Okay.
yeah. So here, if you I said that this my first time giving this talk, so still premature. But like here, if you just look at this profile ODE, this is the a very simple example ODE. But this is just an eigenvalue problem. There's no source. The a zero in particular is a solution to
Okay. Okay. Okay.
Yeah.
Thank you. Then.
Thanks. Great questions.
We have a question from Aditi. How does this scale on a system of equations with varying scales, with initial conditions given at the point of singularity?
Oh, is that? Oh,
It's on the chat.
it's
Yes.
on the chat. Okay, let me take because I think it's a very long question, and with initial conditions on the, yeah, I'm not sure. What do they mean by initial condition given at the point of singularity? But like I think to me this question there's two parts. How does this scale on the system of equations with varying scales? Okay, I think that's very hard because our message, think about it, our message to start with. Why do you solve a profile equation? Because profile equation, the solution supposedly is going to be nice. If the profile solution is of multi-scale, if the solution is of multi-scale, this means that your answers is not correct. This means your true solution might not be self-similar. You need to come up with a better answers because think pings, the way I think of it, pings is very powerful, but it's a numerical method. So if the problem is multi-scale, then you have to do multi-scale tricks to come up with that. You cannot magically hope your pings to be able to deliver you a magical multi-scale solutions. Secondly, initial conditions given at point of singularity. I don't know what exactly
I'll
you mean by that.
explain.
Oh, yeah.
So, I mean, say for instance, you have a Burger's equation, right? But the initial condition is like a step function.
Oh,
Um, does that make sense?
yeah.
So,
That makes sense. Yeah.
yeah.
Yeah. A great question. I think so again, two answers. First, it's a bit tangent to what we are doing here because what we are doing is a really, at least so far for the paper by itself, it's really focused on the profile equation. So it's again, it's gonna be have nice solutions. So if it's an initial condition already singular, then I don't know. Then you probably need to do appropriate like a weak formulation or appropriate other tricks, which is not within the scope of what we're doing here. On the other hand,
Um,
uh,
but like, can you not sort of develop a self-similar variable that captures that sort of discontinuity at the initial time? Or
yeah. That's a good question. So again, our methods there's two stages. First, you come up with a good answers. So in all I've described, the answers is self-similar. You can of course go beyond self-similarity as I've taught in my more math works. But first, you come up with a good answer. So in your case, if you think your initial condition is a Dirac and your good answer is self-similar, then you plug that in. And after that, the resulting equation should be nice again. The way I think of it, if you're, if, okay, you guys can feel free to correct me if I'm wrong. The way I think of it, the thing you feed into your pings, or basically not just pings, any numerical method, the way you affiliate to it, should be nice. Like if you're asking a numerical method to solve a thing that is not nice, by nice, I'm not saying like constant. I'm just saying a smooth. Yeah. If it's not nice, then your numerical method cannot solve it. Then your answer is wrong. Then you should work on better answers. So does that answer your question? So you want to come up with a good answers of representing your singularity in your case, and that for now, we have to do it a case by case, pen and paper. For now, there's no way of automating a good answers, but potentially, you could also argue that you can ask some language models or something of sort to come up with a good answers of your singularity and do it in an intuitive way. Yeah.
okay, thank you so much.
Thanks.
Thank you. Do we have more questions for the author?
Yes, I just have one short question. Is there any ansatz for compressible Euler equation that
Oh,
you?
for compressible, yeah. I mean, I don't know. First, I don't work on compressible, but I'm aware of the works. I think what you have in mind is probably a very important breakthrough by a quadruple of mathematicians, Frank Moe, Pierre Raphael, Igor Aronofsky, and Jeremy Schaffel. Basically, 3 years ago, I want to say, like a couple years ago, what they proved the shock formation of compressible Euler, a very essential thing they use is they use the link from compressible Euler to Burgers, essentially, the way I understand it. So again, in their case, their profile is essentially one-dimensional. Unlike that's understandable because for incompressible equation, you cannot have one-dimensional. Come on, if you're just one-dimensional, there's no notion of incompressibility. So incompressible equations, you have to intrinsically have higher dimension. For compressible, I think what they use is a one dimension, but I might be wrong. I think I'm correct, but I'm not an expert.
So when you say one dimension, it's like you have time and another extra dimension?
No. As I was saying, in this self-similar framework, there's already no time. Yeah, there's no time.
Okay, so it would be something similar to this profile ODE for implicit burgers?
Yeah, a lot more complicated. I think it's a system or something, but it's one-dimensional.
Okay.
Yeah, but I'm not an expert.
Okay, thank you.
Thank you, Ahmed, for the question.
Oh,
We
yeah.
have another question from Rutvik. Why is it's also on the chat? Why is
Yeah.
it that the residuals are generally larger on the boundaries? Are the boundary conditions not imposed as a hard constraint?
That's a very good question, but can I? Oh, okay. Yeah, that's a good question, but let me clarify. So here, are you talking about a Busnex or a burgers? Because for burgers, I think it's okay. For burgers, it's okay. For Busnex, on the other hand, yeah, as they're asking, it looks like the residual is a larger on the boundary of the axis. But I want to clarify that this axis is not a physical boundary. This is just yeah. Long story short, this is not a physical boundary. It's larger because first we sample more points around the origin. Secondly, we know that the solution. So if you go back to my computer assisted proof methodology, we know that the solution is more important at the origin. At the far field, outer and outer far field, it has decay. So at high level, it's not as important to compute it accurately as compared to the a more like points closer to the origin. However, if you don't impose the boundary condition, because the equation is non-local, if you impose it in the wrong way, then you can totally mess up your computation on the interior. But if you once you impose it correctly, then it's less significant compared to the interior points. Why is that? Because, for example, you can look at this singular weights. The singular weights, the weights are smaller and smaller on the far field. But again, this is singular weights for the semi-linear heat, but it's a similar high-level idea is similar to the Busnex. Yeah, so the far field is the further out, it's less and less important. But still, you have to get it correct. It just the precision has to be a larger, in a quantitative way. The precision has to be better around the origin.
Yep. Does that answer the question, Rutvik? Yes, he confirmed. Yeah.
Thanks.
Do we have any more questions for the speaker?
Thank you, Yixuan, for the good talk.
Oh yeah, thanks, George. Yeah, thanks again, guys, for your hospitality. Yeah,
Thank you so much, Yixuan. It was a really good presentation.
thanks.
Thank you. In that case, I'll close this week's Crunch seminar. Have a nice weekend, and thank you.
Yeah, as well. Bye bye.